Welcome to The Explainer. So, how do you really know if a medical test is working or if an AI is making the right call? Well, today we're going to pull back the curtain on a powerful tool that helps answer exactly those questions, the ROC curve.
All right, to really wrap our heads around this, let's start with something we can all understand, a high-stakes medical decision.
Now, you might think the answer is simple, right? You just count how many times the test gets it right. But it's actually not that straightforward. The real challenge is figuring out the cost of being wrong. See, it's not just about being right. It's about the trade-offs you have to make when you're wrong. Because as we'll see, every test can be right and, more importantly, wrong in a few different ways. So let's talk about those outcomes. For any test like this, there are really only 4 possibilities. Let's break them down.
Okay, this grid might look a little complicated, but don't worry. It's called a confusion matrix, and it's basically just a scorecard for our test. You've got your true positive. That's a hit. We correctly identify a sick person. Then there's the false negative. That's a big miss, and it's dangerous, right? We tell a sick person they're fine. On the other hand, you have a false positive. That's a false alarm. We tell a healthy person they're sick, which causes a ton of unnecessary worry. And finally, the true negative, a correct rejection. We rightly tell a healthy person they're healthy. The performance of any test is just a balancing act between these 4. So let's focus on the first really important number here, the true positive rate. All this is the percentage of sick people that the test actually correctly catches. You can think of this as the benefit of the test. How good is it at actually finding the disease? And now for the flip side of that coin, the false positive rate. This is the percentage of healthy people that the test incorrectly flags as being sick. This is the cost of our test. How often does it cry wolf and cause all that unnecessary stress? And this is where it all comes together. The ROC curve is basically just a graph of this exact relationship. The story of a test's performance, plotting the benefit, that true positive rate, against the cost, the false positive rate. So let's actually visualize this trade-off. We're going to build the graph at the heart of all this, the ROC space, right from the ground up, so we can see what it's really telling us. Okay, so just picture a square graph. Along the vertical y-axis, we plot the benefit, our hits, from 0 to 100%. And then along the horizontal x-axis, we plot the cost, our false alarms, also from 0 to 100. Pretty simple, right? The performance of any given test can be plotted as a single point somewhere inside the square. Now, see that diagonal line cutting from the bottom left to the top right? That represents just pure random chance. If your test performance lands anywhere on that line, well, you might as well be flipping a coin. And if it's below the line, that's even worse than random. Yikes. But this point up here in the top left corner, this is the holy grail. It represents a perfect test, 100% hits, 0% false alarms. It catches every single positive case without ever crying wolf. The closer any test can get to this corner, the better it is, period. Okay, so a single point on the graph is one test result. But we've been talking about the ROC curve. So where does the curve actually come from? Well, it shows us the full range of a test's performance. So here's the really cool part. Most tests aren't just a single point. They have a threshold that you can actually adjust. So imagine a blood test where we're looking for a certain protein. We have to decide what level counts as high. If we set that bar really low, we're going to be super sensitive. We'll catch more sick people for sure, but we'll also get a lot more false alarms. But if we set the bar really high, we'll get fewer false alarms, but we'll end up missing more sick people. As we slide that threshold up and down, we literally trace out this characteristic curve on the graph. So when you look at one of these charts, the key takeaway is actually pretty simple. You are looking for a curve that bows up and to the left, hugging that top left perfect corner as tightly as it can. A curve that gets closer to that perfect spot just means you have a better test. It means for any level of false alarms you're willing to accept, you're getting way more correct hits in return. And this tool has a pretty fascinating history. It's not some brand new data science thing. It was actually developed way back in World War II to help radar operators tell the difference between an enemy aircraft and just random noise. From the battlefield, it jumped over to psychology, then it became a huge deal in medicine and radiology, and now it's an absolutely essential tool for evaluating modern AI and machine learning models.
All right, so looking at the shape of a curve is great for getting a feel for things. But what if you've got 2 or 3 or 10 different models and you just need to know which one is best? What if you need a single simple score to compare them?
Well, it turns out there's a really elegant way to do just that. We can literally just calculate the area under the entire ROC curve. This one measurement boils that whole complex trade-off down into a single, powerful number called the AUC, or, you guessed it, area under the curve.
The AUC score is super easy to interpret. It goes from 0.5, which, remember, is no better than a coin flip, all the way up to a perfect 1.0. So a score like 0.92, that's really, really good. That's an excellent classifier.
But here's a really cool and intuitive way to think about what that AUC number actually means. An AUC of 0.92 tells you the probability that the model will get it right. If you take one random positive case and one random negative case and show them to the model, there's a 92% chance it will correctly rank the positive one as being more positive than the negative one. It's a pure measure of how well the model can tell the two apart. And this is why AUC is so powerful. It makes comparing models dead simple. Just look at this graph. We've got 3 different models here, each with its own curve. It's obvious that the red curve has the biggest area underneath it, right? That tells us, at a glance, that it's generally the best performing model out of the 3. So when you boil it all down, from those radar operators in WWI to the most advanced AI today, the ROC curve is this timeless, brilliant tool for making better decisions when you're dealing with uncertainty. It doesn't give you a magical right answer. What it gives you is a crystal clear picture of the trade-offs you're facing.
Which brings us to a final critical question. In the fight against a deadly disease, what's worse, a false alarm or a missed case? The ROC curve can't answer that for us. It doesn't tell us which trade-off is correct. All it does is lay out the menu of options. It shows us what's possible. For a deadly but treatable disease, yeah, we'd probably accept a lot of false alarms to make sure we never ever miss a real case. For something less critical, maybe not. The curve just shows us the choices. That final critical judgment, well, that's still up to us.